Again, second lecture.
Okay, thank you. Just switch on the microphone. Okay, so let me remind you what we did last time. So we talked about Levy process. So I introduced them last time. I defined what those were. So if you don't remember or you haven't been here, Levy process, it's a stochastic process with stationary independent increments. If you've never seen them, think of random walk in continuous time. These processes are described by characteristic exponent. So it's a function psi of z. Essentially, it's a logarithm of characteristic function. There is a Levy-Hinchman formula which tells us that for any Levy process, psi must be of this form. Okay. And this has all the information about the process. So basically, that's the diffusion term, which tells us whether Brownian motion is there or not, the linear drift. And the measure pi tells us about the jumps of the process, the frequency and the size of the jump. And so everywhere in this lecture, E of q will denote an exponential random variable with parameter with mean 1 over q, which is independent of x. And we also defined supremum and infimum, so we just take them pathwise. So we have trajectory of the process, we stop at time t, look at the highest point the process reached and the lowest point. So the Wiener-Hopf factorization for Levy process was a probabilistic result that stated that something was independent and had the same distribution. But in analytical terms, that's the statement. So we look at the characteristic functions of supremum and infimum. And these functions essentially solve the Riemann-Hilbert problem. So on the real line, they're connected like this. And phi plus is analytic in the upper half plane, phi minus in the lower half plane. And so the problem is that we know psi. We want to find phi plus, phi minus. Okay, so to convince you that's an important problem in probability, these factors phi plus minus, they actually have a wealth of information about the underlying stochastic process. So it's often very important to be able to find them. But not only just to find them numerically, even though it's useful too, but really in most applications we want to have them explicitly, because we want to do then inverse Laplace transform or inverse Fourier transforms in some variables. We really want to get distributions. Okay, so really the goal is to get some kind of explicit formulas for those Wiener-Hopf factors. So why do we want to do it? Well, because, so remember, these are characteristic functions. We can invert Laplace transforms and get distributions of supremum and infimum. Sometimes we can go further, and because these guys are essentially Laplace transform in time of the supremum at fixed time, we can do another Laplace transform inversion and get distribution of supremum and infimum at a deterministic time. And in general, many other quantities in stochastic processes can be expressed in terms of Wiener-Hopf factors. So for example, remember tau h plus is the first time the process reaches level h. So it starts at 0, moves somehow, and the first time it crosses level h, that's tau h plus. And x tau h plus minus h, that's an overshoot. So by how much the process jumps above the level h. So this formula essentially gives you the joint Laplace transform of these two random variables in terms of the Wiener-Hopf factors. So once you know Wiener-Hopf factors, you may try to figure out the joint distribution of these guys. And there are tons of other identities of this sort. So once you know the Wiener-Hopf factors, you just have open door to start computing various things of interest. Okay, so how do we find the Wiener-Hopf factors? So there are two methods. One is probabilistic, and then later I would show more analytical method. So probabilistic method is the following. So essentially, we just guess some solutions to this Riemann-Hilbert boundary value problem. So we just identify two functions f plus, f minus, which are analytic and corresponding half planes. And then we check that these functions are actually characteristic functions. Sorry, it should be function here. Characteristic functions of infinitely divisible random variables. And because we have uniqueness of this factorization in the class of infinitely divisible random variables, we're done. Okay. So here's an example of how this works. Probably the simplest example is take a Levy process, Brownian motion with drift. Then characteristic exponent is just quadratic polynomial. So when we solve equation psi of z equal to q, this polynomial will have two solutions. They're both purely imaginary, and one in the upper half plane, one in the lower half plane. Okay. And then after some algebra, so first I introduce positive numbers lambda 1, lambda 2. So these guys are both positive. And I can factorize this function as product of these two functions. And note that this guy is analytic in the upper half plane, this guy is analytic in the lower half plane. So they would be natural candidates for my Wiener-Hopf factors. Okay. But then you ask a question, so can you think for random variable of a random variable psi for which characteristic function is of this form? So does there exist such a random variable? Well, of course there does. This random variable is exponential, so it has probability density function f psi of x, which is lambda 1 e minus lambda 1x for x positive. And then from probability we know that exponential distribution is infinitely divisible, so we're done. So we have identified, so basically we have factorized this function to product of two characteristic functions, which are characteristic functions of infinitely divisible distributions. And this allows us to conclude that for Brownian motion with drift, if we stop it at an exponential time, then both supremum and infimum will have exponential distributions just with different parameters. Okay. So let's try the strategy for another class of process. So hyperexponential or meromorphic process. So remember, these are the processes for which the Levy measure is just a sum of exponential functions. So if we look at Laplace exponent, it's just more convenient to work with this function small phi. It's a simple time change of characteristic exponent. It's either a rational or meromorphic function of this form. Okay. And these are very special meromorphic functions. They belong to the class of peak functions. Well, not this function, but function phi of z over z is a peak function. So it maps upper half plane into itself. Okay, it's not hard to show. And then from here you can deduce that this equation has only real solutions. Okay. Not only it has only real solutions, but also the solutions zeta and zeta hat, they interlace with the poles of that meromorphic function. Okay. So what this gives you in terms of characteristic exponent is that, so remember I have this function q over q plus psi. So this tells me that this function is meromorphic and has poles and zeros lying on the imaginary line, and poles and zeros interlace. So okay, here they don't, but otherwise between each two poles I'll have a zero, and vice versa, except for the origin.
And is that important?
Yes, that's super important because it allows me again to, well, so first I can separate the product over poles in the upper half plane versus the product over poles and roots in the lower half plane. So I can kind of divide them into two products. One will be analytic in the upper half plane, one in the lower. But because they interlace, again, I can use probabilistic argument to show that these are actually characteristic functions of infinitely divisible distributions. Okay, so let me just show you the formula. So I take this product over, so in this case, all poles and roots lying in the lower half plane. Now this function is meromorphic, well, sorry, analytic in the, well, I have too many half planes here. Okay, that's in the right half plane, but you see here I have IZ. So without IZ it would be upper half plane. But now, because these guys interlace, I can do the partial fraction expansion of this function, and I'll get coefficients which are positive. So basically, again, I can go back to probability theory and say that this thing is just a mixture of exponentials. It has a distribution of a mixture of exponentials, which is known to be infinitely divisible. Therefore, I can apply uniqueness argument to conclude that these are my Wiener-Hopf factors. Okay.
But I don't quite understand why we need to show the. I mean, we know they're unique up to a constant.
The Wiener-Hopf factors?
Yes, from a point of view of complex analysis.
We don't yet. We'll know this after my next slide. But if you have, so a priori, I'm just factorizing this into two functions. And I'm not requiring anything else of these functions besides them being analytic in the upper half plane, lower half plane. So I can always multiply this function by exponential of some entire function.
Okay, so
right?
you have no growth restriction.
Yes, at this point I have no other restrictions. I'm just using analyticity and the fact that these guys must be characteristic functions of infinitely divisible. Okay.
And the inverse doesn't have to be analytic.
Which inverse?
The inverse of the plus function doesn't have to be analytic in the upper half plane or not.
Inverse, you mean functional inverse?
Does it have zeros?
No, it doesn't. Because we know that this guy is a characteristic function of infinitely divisible, it doesn't have zeros. Yes, it's zero free. Okay, so here's an example where this probabilistic method breaks down and where we actually need this more analytical approach. So consider a Levy process with jumps of rational transform. So it's a pretty big class. Here we just require that psi be a rational function. Okay, so if psi is a rational function, then the same is true for 1 plus psi. So we can factorize it as product over zeros and poles. Okay, and then we do the same trick. We separate roots and poles which are in the upper half plane from the roots and poles which are in the lower half plane. Now, this would be our natural candidate for phi plus, because it's analytic in the upper half plane. This would be our natural candidate for phi minus. But now we have a problem that we can't really say that this is a characteristic function of an infinitely divisible random variable, because we know nothing about the roots and poles. Well, we can find the poles of this probably quite easily, but the roots, they could be complex, they could be anything. So at this stage, probabilistic argument breaks down. But luckily, we can prove a fairly simple analytical uniqueness result, which is essentially what was done yesterday in the lecture using Plemielch theorem. Okay, so here is the result. Assume we have found two functions, f plus and f minus. So we have found two candidate solutions to Riemann-Hilbert problem, which are analytic and continuous and zero free, because we know that phi plus and phi minus are zero free. So we require these guys also to be zero free. And we put a growth condition of this sort. So logarithm of the function doesn't grow faster than a linear function. Okay. Then these are my Wiener-Hopf factors. Okay. And the proof is fairly simple. Again, it's almost the same proof as was shown yesterday. We just define this new function capital F. And this function is well defined everywhere. Well, it's well defined for real values of z, because both of these guys come from solutions to Riemann-Hilbert problem. It's analytic by construction. It's zero free by construction, and it's also continuous everywhere. So therefore, it's analytic in the entire complex plane. But because it's zero free, it means that logarithm is also analytic. But because logarithm of this function satisfies this growth condition, by Cauchy estimates for derivatives, we can conclude that it's a constant function. And this constant function is 1 because of this condition here. Okay. So basically now all we need to do is we need to find candidate solutions, and then we need to check that the solutions are analytic, zero free, which is usually quite obvious from construction. And the main part is usually to prove this asymptotic condition. And so going back to process with rational characteristic exponent, in our case, it's obvious that that growth condition is satisfied, because when we take logarithms of this guy and this guy, they'll be, well, growing like logarithm. They'll be growing slower than a linear function. So therefore, these are the Wiener-Hopf factors. Okay. Okay, so now with this result, we can move on to stable process. So let me remind you what's a stable process. So it's a process which has characteristic exponent, which is just a power function. Okay. When z is negative, it's just a conjugate of this, and with absolute value of z. So we'd like to find distribution of supremum and infimum at exponential time and also deterministic time. But in this case, so remember, stable processes have scaling property. So the process at time ct has the same distribution as c1 over alpha xt. So I can always scale a constant from time. Essentially, I only need to look at distribution of this random variable and this random variable. And for infimum, it's kind of the same problem. I can just switch rho to 1 minus rho, and I'll get from here, this will become infimum, this will become infimum. Okay, so therefore, we focus on finding these Wiener-Hopf factors. And so, again, a brief history of what was done for stable process. Basically, it's an old problem. People started looking at this back in 1950s. And to give you an idea, so Levy processes were introduced in 1940s. So stable processes were studied pretty much from the very beginning of study of Levy process. But not much was done since 1950. So basically, here people have done either some very, very special cases when, say, the process has only negative jumps and no positive jumps, what's called spectrally negative process. That's a fairly simple case. I think Heidi has derived an integral formula for the Wiener-Hopf factors. And basically, not much was known until 1987. In 1987, Ron Donny has published a very curious paper. So he actually computed Wiener-Hopf factors for all parameters alpha rho which satisfy this relationship. And by the way, I didn't mention, or maybe I did mention it last time. So stable processes are described by two parameters alpha and rho. And these parameters are in the following domain. So rho is always, well, rho is the probability that xt is positive, so it's always between 0 and 1. And alpha is between 0 and 2. So this rho equal to 1 over alpha, rho equal to 1 minus 1 over alpha. Okay. So this is a set of admissible parameters A. So what Ron Donny has done is, so he proved that, so take a point here in this set, so alpha rho, and if this alpha rho satisfies a strange relationship where k and l are integers, then we can calculate the Wiener-Hopf factors. So how do we calculate it? In terms of a certain special function called Q-Pachammer symbol, defined like this. And here is the formula. So Wiener-Hopf factor, which is a positive Wiener-Hopf factor, it's a ratio of two Q-Pachammer symbols. And there is a similar formula for the negative Wiener-Hopf factors.
Can you go to the previous page?
So, why is this a strange result? So this condition here that rho is equal to L over alpha minus k, you can think of this as follows. So pick any L, take any, okay, so first of all, fix alpha, and ask yourself for which values of rho this condition can be satisfied. then fix L and choose K so that rho is between 0 and 1. So essentially I'm taking fractional part of L over alpha. But now if alpha is irrational, this will be a dense set. So basically for every irrational alpha, I have a formula for the Wiener-Hopf factor for a dense but countable set of rows. Essentially I'm covering my whole parameter space with a dense set for which I have explicit formula, which is a very strange result, right? You don't see such results often. So just to give you another point of view, let me plot these curves. So I'll plot the curves rho equal to L over alpha minus K for different L's. Okay. So here's what they look like for absolute value of L less than 20. So that's my admissible parameter region, and here are these curves. And if I increase this to L less than 100, you see that they're really dense in the set of all parameters. Okay. So something strange is going on, right? We have this very natural model, and we know the Wiener-Hopf factorization for a dense set of parameters. And clearly something here depends on whether parameters are rational or not. Like you see, when alpha is 1, we have a big gap that nothing is known. Okay, so how do we solve this? Okay, so let me again state the problems we want to solve. So we want to find two functions, f plus and f minus. So they're analytic in the upper half plane. So f plus is analytic, continuous in the closed upper half plane. But also, I'm going to require that this function be positive on the imaginary line. Where does this requirement come from? Well, because the Wiener-Hopf factor at IU is just the Laplace transform of supremum. Okay, so by definition it's positive quantity. Okay. So f plus is analytic in the upper half plane and positive on the imaginary line. F minus the same but on the lower half plane. And these two functions satisfy the following Riemann-Hilbert problem. So for z positive, they factorize like that. For z negative, they factorize in the same way, but with a conjugate. Okay. So how do you find such functions f plus and f minus? Okay, so our strategy is first we would derive a functional equation for these functions. We would guess a solution, and then we would apply that uniqueness result to show that our solution is the right one. Okay, so let me introduce okay, so I'm going to introduce two functions, g plus. So I'm going to change variables from z to EW. Okay, and lambda AB, that's a strip in the complex plane between A and B, open strip. So with this new notation, so going from this result from function f to function g, now g plus becomes analytic in a strip between 0 and pi. Okay, and it takes real, actually positive values on this line in the middle of the strip. G minus, okay, so that's for G plus, and G minus is analytic in the strip 0 minus pi and takes positive values in the middle of the strip. And on the real line, these two functions satisfy this condition. So first, I'll show that these functions can be extended to meromorphic functions in the entire complex plane. So here's how it's done. So first, from the Wiener-Hopf equation, I rewrite G plus in terms of G minus. Now, G minus is analytic here. This function is meromorphic everywhere. Okay, so therefore, I have extended function G plus into a bigger strip from minus pi to pi. Okay. But now I know that G plus takes real values, actually positive values on this line. So I can use Schwarz reflection principle and extend G plus to an even bigger domain. So by Schwarz reflection principle, I extend G plus into a strip from minus pi to 2 pi. Okay. Now, you can guess we do the same for G minus. So we rewrite the Wiener-Hopf factorization in terms of G minus. Now, I know that G plus is meromorphic in this whole strip. So G minus must be meromorphic in at least as big a strip. But because G minus takes real positive values on this line, I can again use Schwarz reflection principle, and I can analytically continue it into a strip. So it's 2 pi between minus 3 pi to 2 pi. Okay, so that's step 4. And then, as you can imagine, I can go back to G plus, do the same, go back to G minus, and continue going between them until I have extended this strip to the entire complex plane. Okay. So that's the proof that both of these Wiener-Hopf factors, after time change by exponential function, change of variables, are actually meromorphic functions. Now here's the next result. This function G plus solves a functional equation like this. How do you prove this? I change variables in the Wiener-Hopf equation from w to w minus pi I over 2. So I'll get this equation. And then I remember that G minus is real on this line. So when I take real part of both sides, So it means that this thing is equal to its conjugate, right? Because it's real, this must be equal to its conjugate. So therefore, this expression is equal to its conjugate. So I change from minus pi I alpha rho to plus pi I alpha rho, and this is the conjugate of G plus w minus pi I over 2. But remember, G plus takes real values on this line, pi over 2. So the conjugate of G plus at w minus pi I over 2 will be G plus at w plus 3 pi I over 2. Okay. Again, just by, you can say by Schwarz reflection principle. And so now you plug this into this equation, you rewrite this equation, and you get this result. And again, change variables from w to w plus pi over 2, pi I, and you get the functional equation here. Okay, so now we have, we have lots of information. We have meromorphic function. The function is kind of quasi-periodic with period 2 pi. It satisfies a functional equation. How do we solve this functional equation? Well, you find a special function that hopefully solves something similar. Okay. It turns out that, luckily for us, physicists and number theorists have developed a function that just fits perfectly this problem. The function is called the double sign function. What's the double sign function? Okay, there are probably 10 different definitions of it, but this one is kind of the most constructive one. Essentially, it's a meromorphic function defined by essentially a Weierstrass product like this. So P is this expression here, and we're taking a product over all positive m and n. Okay, and we omit the term m equal to 0, n equal to 0, because otherwise we have a problem. So by construction, this function has zeros and poles. So if you take alpha to be a complex number, so here's 1, here's alpha, and construct a lattice with steps 1 and alpha, then this function will have poles in the first quadrant of the lattice and zeros in the third quadrant. Okay, so it kind of reminds you of elliptic functions, right? Elliptic functions would have zeros and poles everywhere on the lattice, but this guy has all the poles here, all the zeros there. Okay. Now in this definition, I haven't told you how to choose A of alpha, B of alpha, C of alpha, and I'm not going to tell you. I'll just show. Well, I'll state that it is possible to choose them in such a way that the function S2 satisfies the following two functional equations. Okay. So it's a kind of doubly periodic function, satisfying the two functional equations like this. And what's more important for us, well, not more important, but also important, is that people have figured out the asymptotics for this function. So this asymptotics will be important when we will be proving uniqueness, and basically it's known. Okay. It's a bit complicated, but quite explicit. Okay. And so now, you see, we need to solve this equation here. So G plus is something divided by something, G plus. I can write this as a ratio of two sine functions, right? By simple algebraic manipulations, I can write this as a ratio of two sine functions, and therefore, well, therefore I get the result that the Wiener-Hopf factor is just product of two double sine functions. Okay. Now, at this stage, I have only guessed the result. But to prove it, actually, now it's not hard. Once you have the candidate solution, you just apply that analytical uniqueness argument. So what you need to do, you need to check that the functions are analytic. That's easy to do because we know where the poles of this function are. You need to check that the function is 0, free, where it should be. That's easy to do because you know where the zeros are. And you need to know this function satisfies certain growth conditions. Easy to do because we have asymptotic equation. So basically, checking uniqueness is easy. Now, well, you may ask, how useful is this? So I was going to try to compute the Wiener-Hopf factor, and I have given you an expression in terms of some special function, which probably no one has ever seen in this room before. It's some complicated special function. So how useful is this actually? Well, surprisingly useful, because, okay, I agree, the function is a bit unusual, not very well known, but has tons of nice properties, and we can pull out a lot of information from here. So one result that we can do is we can actually, just by pure analysis, we can compute the Mellin transform of supremum at time 1. Okay. And this will be computed also in terms of a function which is closely related to double sine function. And then once you have the Mellin transform, now you can attempt to do the inverse Mellin transform and try to get the density of supremum. And that's actually doable. So you can do some simple calculations and find the residues. And what you'll find is the following. So I'm going to define these two sequences. Okay. Okay, there are two gamma factors. Just ignore them. They're there to, well, they kind of ensure that everything converges. But then there are these curious products of ratios of signs. Okay. And you see right away that these coefficients will not be even defined if alpha is rational. If alpha is rational and m is big enough, this thing will have division by 0. So already I see this phenomenon which we observed in Rondoni's result, that this has something to do with number theory, that whether alpha is rational or irrational will play a role in our result. By the way, you can see how number theory actually enters even at the level of double sign function. See, double sign function has zeros at these points and poles at these points. But in our case, alpha is real and positive. And so you see that if alpha is irrational, all the poles are simple, right? And if alpha is rational, we'll have multiple poles. So already things start to break down at the level of double sign function. Okay, so again, we define these two sequences. And so we proved the following result with Friedrich Hubelek, that the density of x1, so the density of supremum at time 1 is given by this convergence series representation, except that it converges for almost all alpha. Okay. I can say much more about what almost all alpha means. So first of all, almost all alpha definitely excludes when alpha is rational. Because when alpha is rational, this series doesn't even make sense. These coefficients are not defined. But surprisingly, it also excludes all alphas which are too close to being rational. So if you looked into Diophantine approximations, you know that there are some numbers which can be approximated by rational numbers too well, and some numbers which cannot be approximated too well. Like quadratic rationals are pretty far away from rational numbers as far as approximations go. And the first transcendental number that was constructed by Levy, it was built especially by the property that it's very close approximated by rational numbers. So surprisingly, this series here diverges if alpha is irrational but very closely approximated by rationals. We can build examples like this. But also, what's nice is that for any alpha which is irrational, I can sum this double series. So I have double series, so think of this as M and N. I can sum it over certain increasing triangles, and I can get conditional convergence. So the series will diverge absolutely, but will converge conditionally for any irrational alpha. Okay. So there is lots of very strange number theory involved in this. And I find this a very unusual result because, again, stable processes are very natural objects, right? They're the simplest possible self-similar Markov process you can think of. Parameter alpha is a very natural parameter. It's a parameter of stability. It tells you how the process scales if you scale time, how you need to scale space. So a priori, there is nothing here that tells you that number theory should be involved. Okay. Okay, but this result here explains, to remember at the end of previous lecture, I posed this question. So I showed you this graph of coefficients Bm for one alpha and this graph for another alpha. So I can tell you now why this happens. So the coefficients Bm actually are these products of signs, and they're obviously very sensitive to what alpha is, right? And so I chose alpha in a very special way. So here I take alpha to be quadratic irrational. It's a number that's written in continued fraction representation as 1 plus 1 over 5 plus 1 over 7 plus 1 over 5 plus 1, etc. So it has periodic continued fraction representation, so it's quadratic irrational number. It's as far from rationals as possible. So that's this alpha 1945. And for the second alpha, I just change this continued fraction representation in just one spot. I just replace this 5 by a very huge number, 42, 42. Okay. And so now by doing this, I ensure that this number is very, very close to a rational number, which is 1 plus 1 over 5 plus 1 over 7. So the difference between this number and this number is tiny. And that's why now the behavior of those coefficients is so wild. Okay. Okay, so last time I promised I'll say something about matrix factorizations. So I'm just going to mention the matrix factorization which arises when you try to solve what's called a double-sided exit problem for Levy process. Okay, so one-sided exit problem here we start a process from some point. Okay, let me start from x now, not from 0. And I have a level somewhere, let's call this h, and the process is doing something. And then at some point it crosses the level. So here I'm interested in such quantities as tau h plus, which is the first time when it crosses the level. I'm interested in such quantities as the overshoot, which is x tau h plus minus h, the undershoot. I may also ask what was the supremum and infimum just before I cross the level. Okay. So basically, any kind of natural question you may ask about how a process exits half line. So for double-sided exit problem, it's the same, but now we're asking how a process exits an interval. Okay, so we have an interval AB, and so again I have the process is doing something, and then it exits this interval here. And so now the exit time tau is the minimum between tau A minus and tau B plus. And basically I want to ask all the same questions, say what was the undershoot, the overshoot, what was infimum, supremum before exit. But now for exit from an interval. As you can imagine, this is a harder problem than that one, right? Because here I can just take the limit as b goes to infinity and recover this problem from here. So that's a priori a harder problem. And actually it's really hard. For Levy process, it's a really hard problem. Almost nothing is known explicitly. Once you go beyond, so the only things which you can compute by a formula are for Brownian motion with drift. There you can derive some formulas. It's easy in that case because Brownian motion doesn't have jumps. So once it exits, it must touch one of the barriers. So it's easy. Another case where you can get formulas are so-called spectrally one-sided processes. These are the processes for which you have jumps of only one side, say only negative jumps. Again, for the same reason, if you have only negative jumps, you can only cross this barrier by touching it. So it's a simpler problem. But once you go to process with jumps of double-sided jumps, there are no explicit formulas at all. You can do some results kind of quasi-explicitly by factorizing certain rational functions if you're dealing with processes of rational transform. But again, you need to factorize them, you need to find the roots and poles. This has to be done numerically. So it's a very hard problem. And doing this for stable process would be really cool. This would be kind of a major breakthrough if someone could say even something meaningful about double exit problem for stable process. Because stable processes are very natural generalizations of Brownian motion. We know everything about Brownian motion. In this case, we know nothing about stable process. Okay, so here is how this connects with Wiener-Hopf factorization. So there is a very nice but fairly complicated paper by Sonia Furati from 2010. And she actually shows that as in one-sided exit problem, everything boils down to factorization of functions okay, so that's what we were doing so far. She's shown that essentially in double-sided case everything boils down to factorization of matrices. Okay. So it's a Riemann-Hilbert problem for matrices. So you, for every fixed x, so think of x as a parameter. This guy, it's a function of complex number lambda. So lambda is in the complex plane. It's analytic in the upper half plane, lower half plane. It meets on the boundary in the following fashion, okay, where psi is the same characteristic exponent. But then this I should not be here, I think. That's probably a typo. And then there are a bunch of growth conditions on the elements of these matrices. So basically, as in the usual Riemann-Hilbert problems, so we have this connection on the real line, and we want to know how things grow in the corresponding half planes. And then once you solve this, this matrix contains a wealth of information about double-sided exit. So it gives you all sorts of Laplace transforms of some kind of functionals related to all these objects. Okay, so the hope is that if you could recover this matrix somehow explicitly, you could maybe analyze it to say something about distributions of all these probabilistic quantities related to double exit. Okay. So Sonia Furati in another paper, she's done it. She used the strategy actually for process with jumps of rational transform. But that's a fairly simple case because, again, when the function is rational, things are easy to factorize. So for stable process, what I try to do is I tried following the same ideas as we've done here. So you can easily follow the same ideas. So in this case, psi would be this power function. Well, you remember it's some kind of complex constant times z to the alpha. Okay. So you can also use the same idea with analytic continuation to show that after a change of variables, z goes to EW, this function and this function are meromorphic everywhere in the complex plane. Okay. And you can basically rewrite this Riemann-Hilbert problem in the following very strange problem for which I don't even know a name. So if someone knows what this type of problems are called, I would be very grateful. So here I'm only considering the symmetric case. So here it's a simpler case, but even for this case we know nothing. So when rho is equal to half. Okay. So the problem eventually boils down to the following one. So we're looking for two entire functions, h and g, which satisfy this kind of condition. And then there are four growth conditions. So these two functions are bounded in the right half plane. These two are bounded in the left half plane. And this has this asymptotic equation, this asymptotic condition, and this has the following asymptotic condition. Again, x is a parameter, so x is fixed, but these functions also depend on x. X is implicit in this function. I have no idea how to even start solving this, or if I don't even see why such functions would be unique. Okay, so according to Sonia Furati's paper, they must be unique. I can't even see this. So if anyone has any ideas and information about this problem, I would be very interested to talk about it. So I think I'm done. Actually, I'm a bit ahead of time this time. So I'll stop here.